Hi everyone, today is the first of two videos on section 8.2, and in section 8.2 our learning targets are the following. We're going to check the random 10% and large counts conditions for constructing a confidence interval for a population proportion. We're going to talk about determining the critical value for calculating a certain level of confidence for a population proportion using a table and using our calculators, and we're going to construct and interpret a confidence interval for a population proportion. In the next video we will talk about how to determine the required sample size for a particular level of confidence. So as you learned in section 8.1, confidence intervals are used to estimate a population parameter. In section 8.2, we're going to focus on estimating a population proportion. And as you can see here with these bulleted items, there's lots of population proportions that we might want to estimate. So what we're going to do is we're going to start with a simple example. And in this example, number one, you're going to assume that I have 500 colored blocks in a container. You won't be able to see these blocks, and your goal is to determine the proportion of the blocks that are green by selecting a random sample of 50 of those blocks from the container. Pause the video and answer these two questions. What is the population of interest, and what parameter are we interested in, and why is it important to have a random sample of blocks? So if you answered that the 500 blocks are the population, and the proportion of them that are green is the parameter in part A, you are correct. In part B, we need a random sample of blocks so that sample is representative of the population, or shall we say unbiased. In this next simulation, what we're going to do is we're going to simulate this situation and see what happens with repeated random sampling. So if you want to follow along, or if you want to work through it yourself, go to this URL, and in the upper left hand corner you're going to see some settings. Set them up the way you see in the bottom corner of your screen. So in this simulation there's a lot going on. If you take a look at the right hand side, upper right hand corner, it says most recent sample. That's going to represent the two possible outcomes for the subject, shall we say, in your sample. They're either going to be green, which is a success, or not green, which is a failure. Below that, the sample statistics, confidence interval midpoints, are going to be the corresponding sample proportion. So what proportion of those 50 blocks were green? And in the center, you will see in just a minute, we're going to have a vertical line drawn at the population parameter, which we theoretically don't know. And then we're going to see the placement of our 95% confidence intervals based on that. So I'm going to start with a single sample, and in my single sample here, the sample proportion p hat is 0.340, and you will see the green block in the right hand corner is plotted at 0.340, and if you move over to the middle graph, you will see that the population proportion is 0.270, and my sample proportion is close enough to that value so that when I go out 2 standard deviations in each direction from that, the confidence interval constructed from my sample proportion of 0.340 actually contains 0.270. So we're going to sample some more and see what happens. We get various sample proportions as is expected because of sampling variability, and it just keeps varying and varying and varying, and we're going to set up the number of intervals to be 50 and see how many of those actually contain the population proportion. So I decided to do 100 confidence intervals instead because I didn't want people to confuse that with the sample size. So here we go. So there's our 100 confidence intervals, and you can see in the lower right hand corner is a simulated sampling distribution, and the blocks shown in red are the sample proportions that were too far away from the population proportion, so that when we constructed the confidence intervals with them, those confidence intervals did not contain the population proportion. So let's go back and answer some questions about this scenario. In 1C, it says, after selecting a simple random sample of blocks, determine a point or single value estimate for the proportion of green blocks in the population. Use appropriate notation. So my first sample proportion was 0.34. And the notation for that is p hat. How confident are you in your point estimate? Compare your estimate with others. Is there variability in the estimates from your samples? Well, we're confident in ours because we know that that confidence interval did contain the population parameter. Compare our estimate with others. When we generated 100 confidence intervals, there were several of them that did not contain the population proportion. Is there variability in the estimates of your samples? Yes, we saw that. In question number 2, it's referring to question number 1. From the previous exercise, we see that there is variability in our sample proportion values. So before we can construct a confidence interval for the population parameter, we need to consider this variability by determining the shape, center, and spread for the sampling distribution of sample proportions. Okay, if we go back here, we can see lower right-hand corner, simulated sampling distribution. If you were to figure out how many possible samples of size 50 we could select from 500, it would be much more than the 100 we generated here. And under the right conditions, our sampling distribution would be approximately normal. So let's start with this. What is the mean of the sampling distribution of sample proportion values equal to? The mean of the sampling distribution of sample proportions is equal to the population proportion, aka sample proportions are unbiased estimators. In part B, the formula for calculating the standard deviation of the sampling distribution is the square root of p times 1 minus p over n. What are the conditions for using this formula? Well, the subjects must be independent in our sample. Do we meet these conditions? Yes, because SRS was used and n is less than or equal to 1/10 of big N. In other words, we are assuming we used a simple random sample in our simulation here, and our sample size was 50, our population size was 500. Here's an important question though. What difficulty do we have using this formula in this problem? Pause the video for a minute and think about this formula right here and think about what we're trying to do and think about how that poses a problem for us. So the problem is this. We are trying to use a sample proportion, p hat, to estimate a population proportion, which we don't know, p. So we can't find the actual standard deviation of the sampling distribution using this formula because in theory we don't know the population proportion. So we're going to do the next best thing, and we are going to use this formula, which is the same formula except we have replaced the population proportion with the sample proportion. And whenever we estimate the standard deviation of the sampling distribution, we call that the standard error. So this is an estimated standard deviation of our sampling distribution. The next thing we're going to talk about is, do we meet the normality condition? We have a similar problem here. We check normality by looking at n times the population proportion and n times 1 minus the population proportion. We don't know the population proportion in theory. So what can we do instead? We can take a look at NP hat. So in our situation, this would be equal to 50 times 0.34, which is equal to 17. And that's actually the number of green blocks that we got in our sample of size 50. And n times 1 minus p hat, which is 50 times 0.66, which is going to be the remainder of those blocks, which is going to be 33. So we do meet that condition. So now we're going to proceed with constructing the confidence interval. Confidence interval goes like this. Sample statistic plus or minus the critical value, we're using 2 because we're constructing a 95% confidence interval, times the standard deviation of the sampling distribution. Well, we're going to use the estimated standard deviation. So 0.34 times 0.66 over 50. So the confidence interval we get would be for 0.34 plus or minus 2 times approximately 0.07, which gives us 0.34 plus or minus 0.14, which gives us a confidence interval that goes from about 0.20 to about 0.48. And as you recall from our simulation, the population proportion was 0.27, and our confidence interval did contain that. So we happen to know in this scenario, which we would not normally know, our confidence interval did contain the population proportion. So let's do a quick review here. The conditions for constructing a confidence interval for estimating a population proportion. The shape of the sampling distribution has to be normal. So n times p hat and n times 1 minus p hat both have to be at least 10. We need for the sample to be random. We need an unbiased estimator. We need the mean of the sampling distribution to be equal to the population proportion. And we need the standard deviation to be something we can calculate using this formula. So we need the sample to be no more than 10% of the population. What I'd like you to do right now is I'd like you to pause the video and do this check your understanding problems, answer these 2 questions, and then we will move on. So when you're doing inference, the first thing that you're going to have to do is check to see if the necessary conditions were met. And you're going to have to read the questions carefully. In actual problems that you are working, check all the conditions. Even if you don't meet the conditions, proceed with the problem anyway for 2 reasons. Number 1, because you need to practice, and number 2, it's possible that you misread something or you miscalculated something when checking your conditions. So, in the first problem it says an AP statistics class at a large high school conducts a survey. They ask the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. 17 students say yes. Well, if they ask the first 100 students, then it's not a simple random sample. In B, it says a quality control inspector takes a random sample of 25 bags of potato chips from the thousands of bags filled in an hour. Of the bags selected, 3 had too much salt. So you can see the simple random sample was met. 25 is way less than 10% of thousands of bags, but 3 had too much salt. So n times p hat is going to be 3, and n times 1 minus p hat is going to be 22. So we don't meet the normality condition. The last thing we're going to do in this video is talk about the actual critical values, the number of standard deviations we need to go out for a variety of levels of confidence. So our confidence interval formula is always the same. The statistic plus or minus the critical value times the standard deviation of the statistic, or the standard error, okay, the estimated standard deviation of the statistic. So we've been saying that the critical value for a 95% confidence interval is 2. Well, it's actually close to 2, and that's based on the empirical rule, which says if you go out 2 standard deviations in each direction, you encompass the middle 95% of the distribution. Well, we're going to refine that process right now and show you how to calculate the critical value for a variety of levels of confidence. So if you want to construct a 95% confidence interval, imagine the middle 95% of the distribution, a normal distribution. As a result, you're going to have 2.5% out here in the tails. So there are z-values that correspond to that. There is a z-value here, which we're going to put a little z star, and a z-value here, which we're going to put a star. And they are actually opposites of each other. You can look up either one of these. But what I'd like you to do is I'd like you to pause the video and look up the z-value associated with the bottom 2.5% or the bottom 97.5%. So ultimately, it doesn't matter if you use the formula sheet, if you use your calculator, if you have this memorized, but you need to know how to find critical values. And this critical value is, this one is actually negative 1.96, and this one is positive 1.96. Technically, you could use either one in your confidence interval because of the plus minus that comes before the margin of error. Just to make sure we get a little bit more practice, pause the video and find the critical values for an 80% confidence interval and a 98% confidence interval using the process that we just did. So if you determine that the critical value for an 80% confidence interval is 1.28 and for a 98% confidence interval is 2.33, you clearly understand this idea. If this is something that you're struggling with, make sure that you ask your teacher. And so to summarize this video, when we are constructing a confidence interval, we need to check our three conditions. Was the sample randomly selected? Is the sample size less than 10% of the population, less than or equal to 10% of the population? And have we met the normality condition? Is n times p hat, our n times p hat, and n times 1 minus p hat both at least 10? If we have, then we can use this formula here in front of you to calculate and interpret the confidence interval.